Greetings. Let us continue our discussion on lack of fit. We were discussing about the effect of lack of fit in statically admissible trusses and statically inadmissible trusses means indeterminate trusses, in which in last lecture we deal with the part of statically admissible frames, and we came to conclusion that the lack of fit will cause the deformation of the member, but it will not develop any stress component in case of statically admissible frames. But this is vice versa in case of indeterminate frames, where the such a adjustment in displacement is not possible, a deformation of members is not possible. The member will be subjected to extra forces here. So we will analyze this structure by considering that the lack of fit member as a redundant member, and we'll find out the effect of this redundant force among all members, among all members. For that, we'll utilize the Castigliano's second theorem, where we'll do the maximization of the uh, strain energy component with reference to the redundant force. So to do this, we will follow some steps. The first step will be the member which has a lack of fit should be selected as a redundant member, and to as a replacement of this redundant member, we will apply a unknown force x as a redundant force there. We will consider the known displacement of lack of fit, or uh, the identified lack of fit as a uh, displacement of that particular joint, okay, and which will be denoted as a dx. The sign convention which it will bear depend upon the type of lack of fit it is having. If it is having a length too short, we will put here negative sign. If it is being too long, we are going to put it as a positive sign. The member forces will be calculated with reference to the maximization of the strain energy component with reference to redundant force. Let's try to understand this concept with reference to a numerical. For that, we'll analyze numerical number 15, which has a statement: while fabricating the pin joint frame shown in figure, the member AC was the last member to be fitted and was found to be 1 mm short of the required length. Find the force in all members of the frame when member AC is forced into position. The diagonal members are each 1000 mm square in area, while remaining members are 2000 mm square in area. Take E is equals to 2000 kilonewton per mm square. The given frame is one brace frame having brace member. The width of the frame, bay width, is given as 1.5 meter, and the bay height is given about 2 meter. Member AC is said to be last member to be fitted, and it was found to be too short. So that's why I have put the member in a dotted line. So as per our consideration, we will consider the member AC as a redundant member, and we will remove from the structure to make it statically admissible, and as in replacement of it, we will apply a redundant force in the same line of action as the member force may move in its original state, so as to have an unaltered effect on the other member forces. So here we will apply X redundant force on both the joints A and C. Let us consider it is being tensile in nature, and we will try to find out the distribution of this redundant force, effect of this redundant force in amongst other joints. So since there is no external loading, we will not go for the any external load analysis. We will go for the effect of this redundant force only directly. Let us say the member AB possesses K1 contribution. Similarly, the member BC K2, CD K3, and DA K4, and the member BD as K5. These are the coefficient which has been developed in the coefficient of the distribution of redundant force among the other members. Now we are interested to know what is the value of this K1, K2, K3, K4. We will go with a K analysis, and for that we will move with a joint by joint analysis method. So first I will consider the joint A. Since there is no external load, there is no question arises about the reactive forces to be developed here. You will see the effect of K only. So we will see effect of X only. So at joint A, we are having three forces there, uh, two member forces and one applied redundant force X. The member force applied redundant force is X, so which is going in tensile nature. To compensate that particular one, we are going to consider the sign convention for the member forces as a compressive in nature. Now after knowing the free body diagram, let's talk about what is the inclination of this redundant force with reference to horizontal. If you want to find the inclination, we can get this one with reference to the geometric relation tan inverse theta equals to tan inverse of vertical by horizontal 2 by 1.5, resulting into value 53.13 degree. We require the cos and sine component of this angle. That's why immediately I will calculate it and put as a ready reference for me. The cos 53.13 result into a value 0.60 and sine 53.13 degree result into value of 0.80. If we apply a static equilibrium equation to this particular joint, we get summation of fx equals to 0, x cos of theta, the horizontal component moving towards the right hand side, and we have considered k4 to move towards the left hand side to have equilibrium here. From this we get k4 equals to 0.60 times the x kilonewton in compression. Similarly, summation of Fy equals to 0 results into a relation x sine of theta minus k1. So actually it is a reverse written here, minus x sine of theta plus k1 should be there, resulting into value of k1 equals to 0.80 x kilonewton compression in nature, compressive in nature. After knowing this k1 and k2 force, we will move to the next joint to find out the another forces, member forces at joint B. We have three member forces K1, K5 and K2. Among this, K1 is known to us. If we apply the static equilibrium equation for this free body diagram, we can get relation minus K5 sine of theta, the component with reference to vertical direction going downward, plus K1 equals to 0, resulting into value of K5 as x kilonewton tensile in nature. Similarly, summation of force in x direction equals to 0 results into a value K5 cos of theta minus K2 equals to 0, hence K2 value comes to be work out to be 0.60 times the x kilonewton in compression. After that, we will move to the joint C. At joint C, we have three forces here. One is the redundant force X and the two member forces meeting at the joint K2 and K3. Among this, X and K2 is nearly known to us. Now, only unknown remains is K3. So, summation of Fy equals to 0 results into a relation minus x sine of theta plus K3 equals to 0. K3 comes to be 0.8 x times of x kilonewton in compression. Once we know all the forces, we will find out the redundant force, and for that we will prepare a tabular format for ready reference here. The very first column will be the members AB, BC, CD, DA, BD and AC. First I will move with the periphery and then we'll go to the diagonal bracings. Length of the member known to us are AB is 2000, whereas BC is 1500, which we can get from the reference figure. The areas of the member horizontal and vertical members was given to us 2000 mm square, whereas for the brace member 1000 mm square was a given value. E value is constant throughout the all members, that's 200 kilonewton per mm square. We have find out the K coefficient distribution of redundant force among other members, 0.8x, 0.6x, 0.8x, 0.6x. They are positive in nature because they are compressive in nature. Minus 1x negative sign imparts here they are tensile in nature. Then we require a product K square L upon AE. Then the product K square L upon AE result into a value 0.64 x square, 0.27 x square respectively. And what finally what I require summative value of this K square L upon A. So what I will take summation of individual product for individual members, and the value comes to be 6.82 x square. After knowing this, we can say strain energy component. Here the strain energy stored under the redundant force is nothing but 6.82 x square upon 2 E. Why AE I have not written? Because I have taken A in the calculation part itself. So it comes to be 6.28 x square upon 2E. So 2E, if I want to maximize it, then what I will do, I will take a partial derivative of the energy stored by the system with reference to the redundant force. So we get a value dou ui upon dou x is equals to 6.82 times of x upon E, where we have considered the component x square, this will be 2 into 6.82 into x divided by 2 times E, 2 get cancelled, what remains 6.82 times of x upon E. If I further substitute the individual values here, it will be E, if I substitute here 200 into 1 and divided by 6.82, resulting into a value of redundant force as a 29.32 kilonewton. After knowing this, we will find the final force. We will know the final force is given as P plus K times of x, where P is 0 because no applied force is there. Then K times of x means here 0.8 times of 29.32 will be the final force in the member. It works out to be 23.46 kilonewton compressive in nature. Similarly, I will do the work product of all other member forces, like for the member BC, 0.6 times of X was that, means 0.6 times of 29.32 I will put here, it is 17.60 compressive in nature. And likewise I will find out the member forces in all members with reference to the redundant force. That completes the analysis. In forthcoming lecture I will talk about the effect of temperature stresses in trusses. Till then, stay at home, be safe, and healthy. Thank you.